Professor Cloudfather here. So let's talk a little bit about laser enclosures. In social media, we see all kinds of interesting discussions. So it seemed to be important to actually bring some science into this. Um, if you talk to folks that deal with commercial air systems, in my case, it's been with data centers, but the basic physics are the same. We have multiple things we need to do with our enclosures. The first thing we need to think about is what's the right type of enclosure and where is it located? Because the critical thing that all the vendors have missed is you actually need to get air intake from outside the building directly into the inlet side of the laser enclosure. Because if you don't have the intake port, what this does is it basically cuts the CFM of the fan effectively in half or less. So say you got this really big fan and you need to move 500 or 600 CFM because you have a 855 by 800 enclosure, you're not going to get there. You're going to need a really large fan, even a big shop vac, even a couple of them won't pull enough air through to exhaust to the outside unless you have an intake to the outside. Now, the other principle that's important is in order to maximize flow, the surface area, the square inches or square millimeters of the intake need to match the exhaust, because that way you're moving a consistently sized column of air with minimal compression across the laser enclosure and out the exhaust. Same reason why we match carburetors to exhaust systems in race cars. You're looking for maximum effective flow. Now, other things that cut down flow are things that sometimes we can't do a lot about, but if we use a large enough square area, and typically for a large enclosure like an 855 by 800, you're going to need at least 6 inches in order to get enough volume of air, enough gas exchanges per minute to keep the particulate matter floating. The problem is with the current range of enclosures, they have very small fans. Typically they're 75, maybe 100 CFM for a large volume enclosure. And what happens is, because they don't have an intake, it's just air leaking through the edges of the enclosure, and it's not even close to matching the square area of the exhaust system. So immediately you're now getting efficiency below 50%. If you have an intake, even just in the wall in the room, at least you have pressure equalization going on. And that will improve your efficiency, maybe up to as much as 70%, but it's very variable depending on the volume of the room and so on. If you take the time to actually build an intake plenum and put that to the side of the enclosure opposite of the exhaust, and really what you want is cross flow from this side of the chamber to this side of the chamber. And typically you'll put the exhaust one in opposite corners of the intake so you get cross flow. Now you're beginning to manage the gas flow within the chamber. Another thing that's important to think about is the higher power the laser is, the more debris and gas content is generated from burning the materials that you're working with. And the other thing to think about is when you're using large frame lasers, such as like an X70 or similar, which have large gantries, you're working with large objects. And so your run times are much longer than they are with a small laser that is maybe doing 100 millimeters square or 150 millimeters square. When you start talking about a workpiece that is 840 by 780, that may take 10 or 12 hours to run, depending on what you're doing. And so you have all this massive gas and burning going on at all times. And so that's why it requires some different thinking in terms of how we're managing gas flow within the laser enclosure and also within the room or the building. Now, if you have an open garage, you don't have a big problem because obviously the square inches or square area of the door, if you have it open 2 inches, is much larger than 6 or 8 square inches. So that becomes your intake into the room. But for folks that are working in apartments or working in a room that's inside a house, which are generally fairly sealed, if you don't have the intake manifold attached to the enclosure, you don't get enough gas transfer. So those are some of the things we need to think about in terms of the enclosure itself. Now, for enclosure sizes, you need to do some experimentation, and you actually need to watch through your viewports what the gas is doing. And the way enclosures that I've been working with, I've now built 4 different prototypes and have been actually watching smoky materials like garbage plywood, which is really smoky and catches on fire frequently. And I've been watching how the gas migrates from the intake side to the exhaust side. You can actually, if you watch carefully, you can actually see the plumes. You can see the direction of the gas from one side to the other. And then, of course, you're constantly tinkering. In my enclosures, I actually have side panels that I can do different experiments with in terms of building, for example, an exhaust collector on one side and an intake port on the other side. And the intake port I'm currently modifying now to actually put in vanes so I can actually direct in my primary work area a second set of fans. I actually have a set of intake pressure fans. And what this does is it allows me to point the air, basically shape the wave going across the bed to my primary work area, which is at X and Y 00, plus 51, plus 200, which is in this corner right here. And so I have a plenum on each side that goes the length of the enclosure. I have ports cut into them that are 4 inches apiece. And then I'm starting to put vanes on them, and I can move the vanes depending on how big of a workpiece that I'm working on. The collector is basically a square box that goes like that, and then it goes out. My exit port's actually right here, but it goes out to the exhaust. This is the fan. What is being used here is a Harbor Freight or a Chicago brand 8-inch axial fan. I particularly like these because they're only about 80 bucks, but they're 2-speed, 1300 and 1600 CFM. They have enough volume where they have a really effective gas exchange, particularly if you properly size the intake and exhaust pipes. So my current enclosure, which is currently a 6-inch intake and outflow, in the next revision, because I'm waiting for my 3D printer, I'm going to build a 3D printed enclosure. When I redesign that, the plenums will be upsized so they're 8 inches in and 8 inches out for area. They will have director vanes on the intake side so I can control the gas flow across the bed. The other thing that the vanes do is I have two different types of vanes. There's horizontal and vertical. The horizontal ones are actually important because I want the airflow pushing the gases away from the laser head. And there's a whole bunch of different reasons for that, but the biggest reason is to keep the hot gases from recycling through the fan on top. Now in my lasers, I have built a laser filtering system where instead of taking intake from the top, it takes it from the four sides of the top. There's a three-stage filter in the top of the laser. Then in the bottom of the laser, there is another filter, which I've shown in some of the videos. And that basically has two purposes. First of all, it redirects the air from the fan in all four directions. It actually pushes the smoke plume away from the laser body by about almost 200 millimeters. And so what happens now is the gas never actually gets to the top of the laser. And people will question and say, well, does that really work? Well, from a real world example, I've been running now for about 5.5, 6 months, and I've been actually checking the laser daily to see if it needs to be cleaned. With the filters, because they're white, I can see on the outside of the filter if I'm starting to accumulate material. And I know that I've improved the gas flow through the director vanes, getting enough flow across the bed. And I can actually watch the laser burning through smoky materials. And you can see that the gas plumes are flat across the bottom. Another piece that's important is if we look at the laser filter system, this is a laser, this is its fan. And on the bottom, we have another filter that wraps around here, but this is a blast shield. And what the blast shield is doing is it has a slightly larger hole than the cone. So you get cool airflow here, which is pushing out on the work surface. The blast back, which comes from burning, normally cycles like this in an unfiltered laser. What has happened is because we have the exhaust of the laser head itself, the intake now taking air this way, this parasitic flow has been stopped. So now we have clean air that's filtered through a three-stage filter going through the fan, which keeps the PC board and the laser itself clean. It also significantly lowers the temperature. I borrowed a FLIR scope and we took a few pictures of it, and we noticed that there was almost a 20% drop in temperature, even when I'm running 100% power in 70-watt mode. Between that and the blast deflection going this way at the bottom, and the blast shield protecting the laser from getting materials build up in the bottom. And if you look carefully at your laser over a period of time, you find it's dirtier at the bottom. There's a whole bunch of stuff that gets built up in all the electronics and the heatsink underneath. By deflecting the blast in a different direction, you now have these columns of airs in all four directions, pushing air that is filled with hot debris away from the laser body. And the impact of this is the cleaner your laser is, the lower the temperature, the less stress the components have. Even your connectors last longer because connectors also suffer from heat stress. So in combination with having enough airflow going through the enclosure, directing the airflow to the primary work area and having the ability to change that, then using a filter system on top and bottom to keep debris out of the laser, you now have significantly extended the life of the laser. Lasers are wonderful things, but if you are not following some of these fairly straightforward practices, you literally have to clean them every 4 hours, particularly if you're working with ceramics, doing anything that is using the laser to chip the surface. And when it's chipping the surface, what it's doing is you're getting pulses of very high energy, which cause fracturing at the surface of crystalline materials. In the case of biological materials, of the various woods and so forth, you're now burning a cellular structure, and you have different types of vapors and debris coming out. But the end effect is, if you still have parasitic reflow, you're going to run into problems of having to clean your laser. And the biggest exposure in lasers and lasers that are dying frequently in the field, which we see all the time in the internet, is the fact that the fans get dirty. They slow down or even stop because no one has cleaned them. And of course, they're constantly sucking in the parasitic hot air and vapors into the fan and coating the electronics. And the problem is electronics and the heat sinks are extremely sensitive to debris buildup and film buildup. And there's two kinds of debris. There's film, which is things like vaporized tar or other types of organic compounds, which coat a film on it. And then there are particulate components, which are ash components, or they're fractured pieces of paint, which are particularly hard to get off because they tend to immediately bind on the internal surfaces of the laser. And then there's things like ceramic and glass, where you're microfracturing the surface, and of course that debris has to come somewhere. The other thing is at the bottom of the laser, if you sit down and you look at what is happening on the surface, you basically have an oval-shaped sphere, kind of like a football, and you're basically burning a little trench. And so if the focal point is right on the surface, the plasma ball is probably maybe 0.2 or 3 millimeters. Depends on the laser, depends on how they've focused all the diodes in the array. In the case of the X70, depends on when you're 35 or 70 mode, which will either be twice as big or half as big, depending on which mode you're in. So when you're thinking about what's going on here, at the actual work surface, you're exceeding 5,000 degrees centigrade. And the problem is the gases that are coming back up are very hot. In fact, if you put a temperature probe right here, right at the bottom of the laser, you can see things as hot as 1,500 degrees hitting the bottom of the heatsink. So there's never enough cooling air in a stock laser to actually offset that temperature difference. And the problem is when you run 100% power at 70 watts, the heat sinks aren't big enough to handle that for any more than a short period of time. Yet if you're doing woodworking, running 1/2-inch ply or 3/4-inch hardwood, your burns may take an hour or two. And the problem is eventually over time there's enough heat buildup between the parasitic activities and the fact that the heat sink simply doesn't have the ability, even with a 55 cubic foot per minute fan, which is what the X70s have, there's not enough airflow to keep the heatsink and the devices within the laser head within what's called the safe operating area. So this is part of the reason why when we look at laser enclosures, we also have to look at the laser itself, and we have to think about how do we get the maximum amount of exchange going between intake and outside on the exhaust side. We have to look about where are we directing the air in the chamber. Then we have to look at the laser itself and think about, well, how's the laser doing? If it's stock and it's in an open room, the gases are simply going to come up and disperse into the room. And the problem with that is literally everything a laser hits is very toxic to humans and pets. They're extremely dangerous. And the problem is you're in the room and there's lots of gases you can't detect. You can't smell carbon monoxide. You can't smell carbon dioxide. You'll smell burning wood, but there's a whole long list of chemicals that typically we find in house fires, and you're breathing the same stuff. So again, getting that out of your room, the room that you're standing in with your laser, is a very critical safety thing that you need to think about. Now, the other thing that we need to talk about are all of these really fancy gas filters. Well, they don't filter gases. They filter particulates. And to their credit, they do a very nice job of doing particulates. But the problem is they do nothing about carbon dioxide, carbon monoxide, and 100 other very toxic compounds that are gas. Basically, you got to get it out of the room or you're going to be breathing it. And it's also dangerous for your pets because the most toxic gases like carbon dioxide and carbon monoxide are fairly heavy gases from an atomic weight perspective. And of course, what happens is you get a stratified layer from the floor to the ceiling of various different types of gases depending on their atomic weight. And so some of the most deadly ones are carbon dioxide and carbon monoxide. And what that does is starts building up from the floor. And that's really dangerous for your pets, and it's also dangerous for you. So for all the folks that think that, oh, well, we can just stick a fan in the corner of the enclosure and just put a little teeny little exhaust port, the problem hasn't been solved. In fact, not only are you getting false economy, but you're putting your health at risk. Now, the other thing about laser enclosures is we need to think about optical safety. And I was really horrified to see a video the other day of some guys, oh, we got a new laser, let's go turn it on. They didn't even have the really poor quality optical density 3 green glasses. They were sitting there just running a laser in front of an open window at 70 watts power, watching it. If it had been a shiny surface, both these guys would be blind. There's no coming back from getting a beam into your eye. And the other thing to think about is if you get your hand in front of a laser that's on, well, the laser will burn through a 30 millimeter thick piece of hardwood. It takes it a while to do it, but your hand, and if you have any question, go grab an American or Canadian hot dog and put it underneath your laser and run a single pass over it, and you'll find that it'll cleanly cut it in half. So if it hits human skin, it's going to go right through the bone. So again, we have to think about physical safety in terms of never putting your hand into an open enclosure or even an open gantry laser, because there's no question you're going to have pieces missing. From an optical perspective, it takes very little laser power, hundreds of a milliwatt, to damage your rods and cones and your cornea. And it happens in microseconds. So there's no time to react. In fact, the exposure will occur. You won't even notice it until several hours later. Well, gee, I really can't see very well. I got these kind of blind spots and oh, my eye hurts. And the problem is that's irreversible damage. Once those cells and the underlying tissues are damaged, they don't grow back. So again, people will criticize me for being a little anal about safety, but it's not worth the risk to your health, your family's health, your pets, or the occasional unexpected visitor, you should never use a laser that is not enclosed in a gantry, or not enclosed in an enclosure. The gantries that are open are very unsafe. So again, it doesn't take a lot to build a chamber. I mean, think about it. It's a piece of plywood on the bottom. It's a couple, 4 plywood sides, some plywood over the back, a hinge, some plywood and a window cut with orange red OD6 plus safety glass, and maybe put a window in front with the same thing so you can see what's going on. Putting some rubber seals or even just reused foam from packaging works for a seal. Putting hinges on the back of the enclosure allows you to open it up, so if you're putting long Y pieces in, say you want to do cabinet doors for RVs, you can slide it in one side and out the front. Of course, you have to make an extension cable to move the controller out of the way over here. But those doors can actually still sit on top of the work surface. It's not 100% seal, but you have enough negative pressure in the chamber going to the outside where a high percentage of vapors are going to stay this way as opposed to coming out this way. You know when you have a really good enclosure design, when you see the smoky gases going from one side to the other away from the laser, but also there's the sniff test. If you can smell what's going on in there, then you don't have enough CFM, or you have leaks, or you have not hooked an intake to the outside and an exhaust to the outside. Again, with the box filters, which they're charging up to $700 or $800 for, all these are is a stack of various different filter types and a fan down at the bottom attempting to suck air out. And of course, that air is going back, and of course, CO2 and carbon monoxide are going right back into the environment you're in. So the hope here is that you've had a little more information to help think about how you want to protect yourself. Lasers are a phenomenally fun tool to play with, and it takes very little effort to build an enclosure. It's well within the skill level of every person that owns a laser, and it really needs to be the first thing you do when you get the laser, because you can't afford to make a mistake. So there are some other things that can be done to improve the lifespan of the laser. One of the big problems is when you're thinking about laser energy, it is coming down at a perpendicular angle. And as we know from the study of optics, even though the surface is irregular, there is a lobe of returning beam that's coming right back into the output lens. If it's a clear lens, it's going straight back into the array of diodes, and this is very damaging. It overheats them, and it basically is throwing the entire laser away when you do that. Unfortunately, there's a whole bunch of people that are selling clear lenses. I'm not going to mention names, but if you want a lens that actually works properly, I've bought maybe 15 or 20 different vendors of lenses. There's only one vendor that actually makes a good lens, and it's atomstack.com. They have a lens that has 2 sides. There's a blue side, which is the side that faces the diode, and there's an amber side. And what the amber side does, the amber side is right here, the blue side is over here, and what it's doing is there's a diffraction grating, and it's reflecting the beam back down on the work surface. And as long as it's not cracked from overheating or lack of cleaning, which is what destroys most lenses, about 95 to 98% of the energy that's being reflected back, which is what we call backflash, is being redirected farther away. Now, there's actually a very simple trick to improve this substantially. because this only works for the amount of time that the output filter, it's not actually a lens, it's a filter, is working. If there's enough heat buildup through lack of maintenance and getting films on this side of the output filter, it heats, and you get all kinds of little pinpoint fractures in the actual diffraction grating. Every time you get a fracture, you're now opening up a window that's bombarding your lasers with reflected high energy. So this is degrading your lasers. It's actually changing the crystalline structure of the gallium nitrate substrate, and over time it will cause the dreaded blue dot. But the dreaded blue dot is what a laser does when it fails. There's two primary mechanisms for laser failure. There's the blue dot where the laser stops lasing, but then it acts like a fuzzy blue LED. That's the most common failure. But there's also the possibility of a catastrophic failure where the damage is so severe that the diffusion and poly in the PN junction actually shorts. And this is a cause of fires, because now all of a sudden your power supply, in case of a 70-watt one, there's 360 watts of power going through your wiring harness and the laser head, and it's basically starting to burn from the diodes back to the pass transistor, which pulses your laser, back through your 36-volt line until the point where the power supply eventually fails, or if it's a good power supply, it actually would do what's called full back current limiting. It's reached its maximum safe current, and then of course it shuts itself off. The problem is low-end lasers have zero protection. They have no ability to know anything about what's happening in the laser. Part of that is an artifact from the fact that GRBL 1.1 is basically an output-only protocol. Basically, you just send G codes with no thought to, well, what's happening. Now, we also have things like ESP codes where you can do queries, but that's only on some lasers. When you start getting in commercial class, there's a whole different arrangement. But in entry-level lasers, we have what are called open-loop systems. And there's no monitoring. We don't know how much current, we don't know the temperature in the heatsink, we don't know the temperature of the diodes. We have no idea what the optical output is because we aren't monitoring that. And there's no protection circuitry. In fact, the controllers are so dumb that you can actually unplug the laser power and the data cable, start a job, and it will completely finish the job thinking it did just fine. So that's what an open loop laser's characteristics are. Now, there are some good vendors that are really starting to gain an understanding of how important closed loop is, which is what commercial systems use, how important that is in terms of safety, number one, because it needs to be smart enough to shut itself off no matter what the controller tells it or anything else. You need to now have an intelligent laser driver in the top of the laser that senses when I'm getting too hot, the output flow versus the input flow of my fan. My fan is slowing down because I have a tachometer. I can see the RPM dropping. That means my fan is heavy. That means it's sitting heavily on the bearings. And it's time to send a message to the user, clean my laser, or at least inspect me. And this is coming. And this will be a differentiator between lasers that are designed to run a long time and lasers that are basically disposable. And there are equal reasons for having both. If you're just entry level and you're an occasional user, you may not even have an enclosure, but if your laser dies, it dies. You go buy another one. But if you've spent several $1,000s in a laser and you're a serious hobbyist or an entry level or small business, the impact of not having safe enclosures, not having properly managed filtering, not having closed loop systems, not having the correct type of output filters on your laser directly impacts your ability to be productive. And non-production is the thing that businesses fear the most. When you couple that with the very difficult problem of finding the correct replacement parts, again, anything you can do to extend the life of the laser through proper maintenance, proper enclosure design, proper gas flow management, proper filtering, proper lenses, means that your laser is going to last a lot longer. The other piece, of course, is daily inspections and daily maintenance, unless you've built systems like this, which can extend your runtime cycle. Right now, I'm running about 10 days between cleaning because the filtering is catching more than enough stuff. And I don't think I've actually cleaned the lens on the output in about 2 months because we kept tweaking the filtering system, monitoring the temperature and looking at the patterns that deposit on the lenses. And we now have enough filtering efficiency and enough gas flow within the chamber to actually keep the laser clean. Now, there is one other thing that laser manufacturers in the hobby side haven't figured out. This is very well known in commercial lasering. You always tilt your laser, your TIG torch, your cutting torch, your welding torch, whatever you're using. All professional welders know, yeah, we do it at an angle because that helps keep the consumables longer. In the case of the laser, what isn't immediately apparent is if you have this perpendicular angle and you put a shim in it, it doesn't matter whether it's X or Y, so that the laser now points to the workpiece at an angle, the reflected beam goes at the reciprocal angle. And so if you look at the X70, if you do 7.5 degrees, you get a minus 7.5 degrees here. And instead of hitting the cone, because here's the cone, it has a little tip like that, the beam goes down, and currently it goes straight up. Well, now the beam is going off to the side. And this is important because all the energy is now hitting the outside of the aluminum cone, and it's no longer going up in the laser. And if you have the blast shield, as this one does, it basically gets deflected off to your work, and then you have a big column of air in all 4 directions because we've changed the exhaust, which further helps keep debris and keep temperature down, and you're never seeing the 1500 degrees going back up into your electronics that you do if you have a laser that doesn't have a blast shield and a bottom filter. So when we look at our enclosure, we have to think of the overall system and the objectives we have. The first thing is health and safety. The second thing is how do we get the longest life cycle of our laser because it's very expensive to replace them. And in fact, in modern low-end lasers, they're using what's called a COS module, which is basically just a die that has a bunch of laser diodes on it. And the problem is if that goes, you have to buy the whole die. And they're typically, for a 70-watt laser, they're about $600–700, and you have to wait months to get one. So again, that's the reason for the discussion with laser enclosures. I'm still continuing on a weekly basis to test the prototypes that I've been working with. I am working with one laser vendor and exchanging information on a weekly basis. And together we're sitting down and looking at how do we evolve inexpensive lasers to long life cycles and extended duty cycles. From a business perspective, the most important thing that any tool has to be is highly available, which means it doesn't fail all the time. And again, regular maintenance. And if you have questions on maintaining lasers, you can check my YouTube channel. I've done several 45-minute to hour-long, everything from cleaning the bed to cleaning the lenses to checking run out on gantries, you know, typical things to take, how to take the laser apart, how to clean it, what to clean, what to use to clean it, those kinds of things. So I hope this discussion has been useful. Industry is slowly waking up to the fact that for a manufacturer to start building the right thing, the big advantage, the huge competitive advantage that the manufacturer will have is a much longer life cycle and potentially a much more manageable maintenance cycle. So again, we hope this helps. We're always open to comments and suggestions. I'd like to thank a bunch of friends who I worked with for many years who are experts in airflow management for data centers and also inside enterprise class file servers, which have extremely complex airflow and very high energy density. These guys are really, really sharp and have been doing the math for years. If you've ever purchased an HP server and looked inside to one of the EP120 power supplies, you'll actually see that that's where most of this information came from. So again, we hope this helps. If you have comments, please send us comments. If we missed anything, please point it out because we're always looking to improve the quality of these presentations. And we look forward to seeing folks be much more successful with their laser. Cloudfather out.